Number 21 we're going to start off from. And remember, this is your test from Saturday, so look at your 2003 multiple choice section. Okay, we're not looking at last night's homework right now. I gave you the packet to check after. We're looking at the test from Saturday. I don't care if you got, even if you're ignorant, you got a 3 on this for now. I want everybody to look up for this stuff. Okay, it doesn't matter where you're at as far as understanding. I want to go over this together. Okay? Because some people did guess at some points without any work. So I want to make sure we understand why things are what they are. Okay, so right now we're looking at 2003. Can somebody read the question for number 21, please? For number 21.
I'll read it.
The second derivative
of a function f is given by f. What's that? The second derivative? How you say it?
F double prime.
Oh, okay. F double prime x times x minus a times x minus b squared. The graph of f double prime is shown above. What values of x does the graph f have a point of inflection?
Okay, so this is the graph of f double prime that's given in the problem. Now, when there's a point of inflection, it's when the second derivative changes sign. Changes sign. That's the key point here. Only when the second derivative changes sign. So, for this kind of a problem here, you were given points A, J, this was A, this was J, K, M, and B. K was where the max was located, right here. M was right here, and B was right here. All right? So, looking at this problem, I know that I have points of inflection when the second derivative equals 0, but it must change sign. So a lot of people might have chosen B and A as their answer. Because when the second derivative equals 0, which it is right here and right here, those are my critical points of the second derivative. But remember, inflection points only occur when the concavity actually changes. And I'm not looking at the concavity of the graph, but I'm looking at the sign of the graph. So, f double prime is positive here. Then f double prime is negative. Then f double prime is positive. Then f double prime is still positive. So, f double prime changes from negative to positive right here at that location.
What do you mean negative to positive?
This is the graph of f double prime. Of the second, no, it's not. That's the thing you're all confusing. Listen carefully. Look at this. This graph is f double prime. So this tells me that f double prime is positive because it's above the x-axis. Then f double prime is negative from here to here.
No, you put from negative to positive.
Sorry. Sorry. Then we go from negative here up to positive again. Then it looks like it gets to 0, which it does, but then it remains positive still. So if I were doing a number line here for f double prime of x, this is what it would look like. I would have A here. I would have the origin right here. I would have B right here. That's all that would matter. Again, this is positive. This is negative. This is positive. This is positive. So, in my second derivative, this is what I see right now. I see that everything is above the axis over here, thus my second derivative is positive. Everything is below the axis over here, thus my second derivative is negative. Everything is above, thus my second derivative is positive. Everything's above, so it's still positive. The key point here is to notice that even though there's a 0 here, this is not a point of inflection because concavity is still positive on both sides. But here and here, there is a point of concavity. So for this problem here, we go from a positive concavity to negative concavity. When you see this change, this indicates a point of inflection. Are we clear on that? Now, when you go from negative to positive, there's another point of inflection. But look at your multiple choice answers. Is 0 one of the choices? When you look at part A, you're going to see A and you're going to see 0. For part B, you're going to see 0 and M. But what did M indicate on this graph? M is this point right here. And a lot of people pick that because it looks like it's an inflection point, but that's the inflection point of f double prime. This is not the original graph. Had this been the original graph, Had this been the original graph, f, then yes, this would be considered an inflection point. Because, Carrie, what I can see it's bothering you already, it's concave down, then it's concave up. So that's an inflection point if this was the original graph, but it's not. The graph that's given is already the second derivative. So what you need to do is make a number line in your mind. You need to make a second derivative number line and look for changes in concavity. There's a change here, there's a change here. So your changes are at A and at 0, the origin. At A and at 0, or choice A for this one. Again, the problem that students have for this problem here, or the issue that most people come up with, is that they look at the graph and they think that the graph is the original function, but it's not here. Again, the graph that's given here is already the second derivative. So start by making a number line and just simply write whether or not the graph is above or below the axis. Above the axis, positive. Below the axis, negative. Above the axis, positive. It hits 0, but then it stays above the axis, positive. So a lot of people think that B is also an inflection point because the second derivative, yeah, it's 0 there. But it goes from positive to positive, thus no change in concavity. If there's no change in concavity, this is not an inflection point. Okay, these are the hardest problems on the test by far. When they give you a graph of a first or second derivative and they ask you to analyze it. Because a lot of people think of that as the original function. But this was not the original. It was given as f double prime. If it was given as the original, Carrie, B would have been the answer. Or location M, sorry, whatever that choice was. Location M. Yeah, yes, I hope so. Did I record, guys? Not for this one? I am. I did it before. I must have forgotten. All right, 22. 22 is a good question, but it's, again, very tough. Very tough problem here. Okay, we have to think about the net change theorem for this one. This has to do with the fundamental theorem of calculus. Okay, remember that thing that everybody kind of shied away from there? Okay, this has to do with that. So, the problem tells us that we're given the graph of f prime. So what are we given? The first derivative, f prime, the first derivative. If it was f double prime? Second derivative. So what is this graph telling us, really? What does it have to do with the first derivative? Whether the function is doing what?
Positive.
Increasing or decreasing, or positive or negative. That's what we're looking for there, yes. Again, this graph is telling us about whether it's increasing or decreasing. That's it. That's all the graph tells us here. So, we're given a graph that looks like a triangle. Okay, I think it's a decreasing graph, right? Yeah. I'm told that the point is at 6 and at 1. So I've got a 6 here and a 1 here. And the problem asks us, it says, if f of 0 is equal to 5, then find f of 1. Then find f of 1. And f of 0 equals 5, find f of 1. So, for this kind of a problem, we have to start by thinking to ourselves. First of all, we're being asked to integrate from A to B, really. Why am I asked to be integrated here? We're trying to find the original function's value. And what are we given here again? The first derivative. We're given f prime here, but we want the original value. So how do you go from a derivative back to the original? You integrate, as opposed to differentiating, going the other way. So here we have to say to ourselves, the net change theorem is really telling us we're integrating. Well, we're integrating from A to B. But the question now becomes, what is A and B? What are those values here?
0 and 1.
Okay, let's go back to our fundamental theorem real quick. If I integrate a function from A to B of f prime of x dx, that is really equal to f of b minus f of a. That was the first thing we talked about with the fundamental theorem. When you integrate a derivative, it's really like you're just applying the limits to the actual function. Because what's the integral of a derivative? It's the actual thing, right? And then wouldn't we put our limits at the end? Let me show the work, because I'm going right to step to step. Here, this is really, the integral of f prime is really f of x. That's what the integral of a derivative is, from b to a. Which really tells me to plug a b in, right? And then subtract it when you plug an a in. So this is really f of b minus f of a. Again, the integral of a derivative is the original, evaluated from the upper to the lower limit, from b to a. You take the b, evaluate it, subtract the lower limit from it. That's just our rule of integration. So what's happening here, really, if we want to think about this as, we are given a value. Which of those values are we given in this problem? F of 0. And what are we asked to find? F of 1. So it makes sense to me to think about it this way. Why don't I integrate this from 0 to 1? Because if I integrate the derivative from 0 to 1, it's really f of 1 minus f of 0. Look at the rule above and see if that makes sense at first. Again, when I integrate a derivative, I get the original function, but now I'm going to make my limits 0 and 1. Why am I doing that? Because I know f of 1, or I'm looking for f of 1, and I know f of 0. I also know this, by the way. How do I know this?
They give it to you?
They don't give it to you. What do they give you, actually?
The triangle.
They give you the triangle. Very good, sir. They give you the triangle. Look at the graph you're given here. Isn't the integral just the area under the curve? So if you want to find the integral of f prime, here's f prime. Just calculate the area under this curve. And what do we know the area of a triangle is? Good, right there. 1/2 base times height. 1/2 times 1 times 6 is just simply 3. So I know that this quantity here is really 3. Okay, I know that the integral from 0 to 1 is the area under the curve. This is 1 by 6. 1 by 6 by 1/2 gives me 3. So this area is really 3. Next, I don't know f of 1, but I do know f of 0. What was that given as? 5. So you put minus 5. Move the 5 over. What do you get for f of 1? 8. Choice D. Again, this problem is one that we didn't go into detail about, which I want to make sure we do now. Because after taking the test myself and doing a few of these, I've noticed that it comes up more often than not. Okay? Remember the part 2, number 4? The one that everybody got stumped on that we all talked about? It was like the integral from 4 to x. And you have to figure out what those values are. It uses a net change theorem also. Okay? So if it didn't make sense here, it probably wouldn't have made sense on the part 2. But it's good that we're practicing it now. So the idea here is this. Whenever you're given a derivative function, and you're asked to find the values of the original, think about integration. Again, if you're given a derivative, so I want you to write these clues down, guys. When you're given f of prime of x, and you're asked to find f of some value, call it a or b or c, use your net change theorem. That's your trigger. Again, whenever you're given a derivative, and you're asked to find the original function's value, think of the net change theorem. Okay, and this right here, this is the net change theorem at the top. Okay, which is also called the fundamental theorem of calculus. It's one of the fundamental theorems. There are 3 of them, really. But I call it the net change theorem. It makes more sense. Because what are we doing? We're looking at the overall change in the function, the net change. Do you remember the problems that we did with distance and displacement? And how if you integrate the velocity, you get the displacement. But if you wanted the distance, you have to look at the negatives and positives. It's the same idea as the net change parts. Okay, it has no change at all. So it's called the net change theorem for that reason. All right, let's go on to 23.
Can you get the light back on?
You can't see? That's pretty good. Go get some more. Good. Number 23. Can I get a reading for 23? Okay, guys.
d over dx, parentheses, brackets, the integral from x to 0, sine.
0 to x squared.
Oh, I thought it was from up or down. Sorry, 0 to x squared, sine of t cubed dt, brackets.
Like that, Kenny?
Yeah.
No, sorry, brackets on the outside of the integral.
Outside the integral?
Yes.
Okay. And you just ask that? It says determine the value of it?
Yes.
Okay. So, again, fundamental theorem here. This is where it comes into play. So, for this kind of a problem here, what the AP exam is trying to get from you is the idea that, you know, if you take a derivative of an integral, what really happens to them? They, like, cancel out, really. But the tricky part here is this. When you take the integral from 0 to some value here, this x cubed, you need to evaluate this. You plug in the x cubed there, right? And then you plug in the 0 there. But if you plug in the 0, what's it going to be? Because sine of 0 is just 0. But if I plug in the x cubed here, I end up getting sine x squared, sorry. You heard me saying that? Is that what you're laughing about?
Yeah.
Sorry, x squared. When you plug in the x squared here, you still have to cube it. So right away we look at this and we say, okay, well, there's really sine x to the 6th. But clearly that's not the answer. Who can explain where this comes from? Of the,
Of
the top one.
okay, of the upper limit, really. It's like a chain rule, yes, it is like a chain rule. But see the upper limit is x squared, what's its derivative? It's 2x, right? So for this one, here's what I want you guys to write down, because again, we didn't go into a lot of detail on this. We talked about this generally. When you're integrating from zero to some variable, it doesn't matter what that variable is, just plug it in. Again, when you're integrating from zero to some variable, plug it in. But then multiply by the derivative of the upper limit. Okay, we've got, again, the test here, the test always does stuff like 0 to x, and that was number 4 on the part 2 again. They did 0 to x and said, find g of 1 and find g of negative 1 that we did.
Wait.
So here you're plugging in the x squared into the actual function for t. You're getting sine of x squared cubed, which is sine of x to the 6th, times by the derivative of the upper limit, your 2x there. Christian.
So we're taking the derivative of the upper limit to
You're really taking the derivative of whatever this is, assuming it's a variable. If it's a number, what's the derivative going to be?
Zero.
A 0, yes. That one's not going to have an effect. It's when it's a variable term up here, okay? So if this is x cubed, just 3x squared, and so forth and so on.
Two things. Is that only when it says dx in the front, and is that only for initial conditions?
There are no initial conditions here. I don't know what you mean.
Wait,
First
is
of all.
from 0 to something is initial?
You mean the limits?
No, because the integral, isn't it from like 0 to
If this, Kenny, if this had been a 2 here, instead of a 0, you would have to have minus at the end here, sine of 2. Remember the idea here that you're just plugging in these limits, but the 0 didn't matter because sine of 0 is still 0? You would have a minus sine of 2 there at the end.
Initial condition,
Okay.
when you have C at the end and you're not giving a limit at the beginning.
Initial conditions, very good, thank you. Because when you do not have limits, you're given some either particular or initial condition, and you're solving for C, that constant. That's when you're going to use initial conditions. Or when you're doing differential equations. When you have the slope fields, that's where initial conditions come in also. Your first question, though, was, is this only for d of dx? Now, yes, it is for d of dx, but there are other ways you can see this. So if you were told, let me just open up a page on Smartboard instead to show you this one. If you were told that g of x is equal to the integral of f of t dt. If you're told that g of x equals the integral of f of t dt, and then the problem said, figure out the value of, or tell me what g prime of x is. Tell me what g prime of x is. Okay, and you would need limits here, but generally speaking. What does this first statement tell me?
gx is equal to the
Read it backwards now.
F of T is the derivative of G of X.
Okay, so if I took the derivative of this side, what would this become?
F of t.
Just f of t, really, right? And what's the derivative of g of x? Isn't it just g prime of x? So if you were asked to do this, this is really just saying f of t. That's all it's saying. Because if g is equal to the integral, then g's derivative is equal to the original function itself. Because you're taking the derivative of g, so then you need to do d dx over here. So you're not always going to see the d dx, Kenny. I'm just trying to show you another interpretation. So here, when it's asked to find g prime of x, they're really saying do d dx of this, which is just back to this value. Now, if you were given, 0 to x here, like that, then it's just going to be f of x minus f of 0. Again, plugging in your upper and lower limits. We don't know if this drops off because we don't know what the function f is.
Why?
We knew in the last problem that f was represented by sine, and sine of 0 is 0, so we ignore this. Okay? Now, if this had not been x, what if this had been ln of x? If this had been ln of x.
Then wouldn't it be like,
I know, sorry. If that had been L of x, what do we got?
would it been 1 over fx?
Okay, close. You're on the right track with the 1 over. But before you do that, you need to actually apply the limits in there. So start by actually substituting the limit in.
So,
Good, Edgar. But what else do I still need now? Why? What is the derivative of the ln x, guys? 1 over x. So you still need a 1 over x here. That's the thing. Okay, you started with the 1 over x. That was right. But it's always times the derivative of that upper limit.
The last time, okay, that's it. So the last time we didn't put it because the 1 was like implied.
Yeah, because remember there was just an x here, Kenny?
Yeah.
What's the derivative of x, though?
1.
So you just put a 1 there.
Okay.
Again, you're only going to be differentiating or putting this derivative when it's a variable term. When it's a constant term, you're just plugging in the constant term. You don't have to worry about that. Okay, so had this gone from like x squared to ln of x, this would be x squared, and then you put a 2x at the end, because x squared is also a variable term. We're going to do more of this with part 2. I think it'll be a little bit clearer when we look at that number 4 problem today after school. Okay, it'll help a little bit. All right, let's continue with this. So that was number 23. Number 24. Can I get a reader for 24? Jasmine, go ahead.
Let x see the function defined y f of x equals 4x cubed minus 5x plus 3. Which of the following is the equation of the line tangent to the graph of f at the point where x equals -1?
Okay, so I need to know right away, guys. These are where your triggers come in that I keep talking about. You hear line tangent. What do you think of right away?
Derivative.
Derivative. Good. First thing to think about is derivative. So let's start by taking the actual derivative. The derivative is just 12x squared minus 5. Are we all clear on that part? To take the derivative, just a power rule there. Now, at x equals -1, if I can find the derivative of x equals -1, I just plug the -1 here. -1 squared is 1, times 12 is 12. 12 minus 5 is just 7. So this 7 is the derivative at -1, which really represents what? The slope of the tangent line. The slope of the tangent line. So take a look at what I did next. I wrote a tangent line, and what did I make the slope? 7, because I knew that was my slope. Now, look at your choices right away first. Are all of your choices have slopes of 7?
No.
So what do you eliminate right away? Good. Even if it couldn't do the rest of the problem, you at least now have a 1/3 chance of guessing, right? So get rid of D and get rid of E. Those are gone because their slopes are -5. Now, after that, I want to say, okay, I have to figure out the value of B, right? But in this problem, I'm told that it's at -1. But to find B, don't I need X and Y?
Well, it's the original.
Good. So I'm told that X is equal to -1. If I plug this -1 into the original, which is not on my page right now, but if I did, this is what I would get in the original. So take -1, plug it into your original function, see what you get for Y. If you get a value for Y that you want, you plug in the X and Y there. Take a look at that for one quick second.
Did anybody else?
Wow.
Anybody else here for me?
Yeah, to make sure good.
So, for this problem, once you get your value of Y, again, you've got -1 for X, you've got 4 for Y. So this tells me that I have the point -1, 4. So plug the -1 in for X, plug the 4 in for Y, and solve for B. B turns out to be 11. You get 7X plus 11. Okay, are we good on that one? Again, tough problem, I know that, but we need to know what the trigger is in the beginning. 25 should have been generally straightforward here. Okay, generally straightforward. So particles are at rest. It says, what does 25 ask about? It says find when the particle is at rest. Okay. So particles are at rest when the velocity equals 0. 0. What were we given in this problem? Were we given the velocity or were we given the position? We were given the position, though we can find the velocity. We were given x of t. If we take the derivative of x of t, this is what we get for v of t, right here. Now, the thing that you want to notice, and a lot of people forget about, GCF, people. When you take out that 6, it makes this problem so much easier. It really does. Okay, again, it really does. Take out the 6. There's no calculator for this, so you got to do this by hand. Once you do that, you're left with this part. Factor t minus 3, t minus 4. You get t equals 3 and t equals 4. Yes?
I didn't do that, but I just didn't think my guy.
That's absolutely fine. Every time, guys. Always quadratic works. Personally, I think it's faster to factor, though, to be honest. Would you agree? Yeah. I'm just trying to help you. But you can always use quadratic. So Edgar just went from here, and he applied the quadratic formula. Okay, he put the quadratic formula in for this part here, which can get a little bit messy, but you can do it. You can always do it. But I would factor the GCF and then factor further. Number 26 is clearly implicit. How do I know it's implicit?
What?
Yeah, this doesn't do that.
Yeah, there's x and y in your function there. Take a look at 26. 3y squared minus 2x squared equals 6 minus 2xy. That's automatically implicit. and they're giving you the point. They're so nice. They could have just said x equals 3, and then you would have to plug a 3 into the original function to get the y value of 2. But they give you 3 and 2. So implicitly, we do this problem. We start. We had, I think, what was the problem? I got my own test here. So the 3y squared, taking its derivative, becomes 6y. But when you take a derivative of y, what do you have to put after it?
dy dx.
Good, dy dx. So for this problem, here's my dy dx right there. Then I take the derivative of the next part, it's just x. The derivative of a constant is 0. Now, what is this? What's going on here? What kind of a rule? Louder? Product rule, very good. Product rule. Why? Why is it a product rule? Yeah, look at the equation, guys. You've got 2xy. So think of 2x as a. So a times the derivative of b plus b times the derivative of a. Again, this is a times the derivative of b plus b times the derivative of a, where a was 2x and b was simply y. And b was simply y. Okay? Now at this point in time, you've got it all set up. And what do you have to do now?
Switch to y prime to the left side.
Yeah, you got to get the y prime by itself. Technically, you could plug in 3, 2 at this point. You could. And then just solve for y prime. If you plug in a 2 here, a 3 here, a 2 here, and a 3 here, that's fine. So plug in all these points, and then you could simply just solve for y prime as a variable. Or you could do what I did and solve for y prime, and then plug in your points, and make sure you don't mix them up, like I clearly did here. Okay? Plug in the points. What I noticed, though, is I didn't get an answer that was a choice when I did this at first, because I mixed those two up.
Yeah.
And then I looked back and said, what did I do wrong? Okay, let me look again. And I had a 24 there, I think, or 28. I can't even see. 22 is what I had? Yeah. So again, I plugged in there. I got my slope of 4/9, choice B. All right. Okay. 27, we never went over. I know for a fact we didn't go over this. So I'm going to show you the rule now. Okay? I'm going to show you the rule now. So, if you ever know that two functions are inverses of one another, because this problem starts off with 27 by saying, let f be defined as, what is it? X cubed plus x, and if g is defined as the inverse of f, determine these values. Okay? So we have to do a little bit of work. Here's the rule that you want to, you know this rule? Sure, absolutely. We never went over this in class, so if you looked it up, that's fine. We didn't even touch on inverses. It's rare that there's a problem in inverses, by the way. Similar, but you're off by a little bit. Okay, so when you want to find the derivative of an actual inverse, it's got to be 1 over. And then don't forget also, here, you're doing f prime of g, it should be in there, because that's the inverse, or whatever it is. F prime of x. Oh, he did show you this one. Okay, good. Good. So let's go over this as a class. Let's just make sure we're clear. If you want to know what the derivative of an inverse function is, the derivative of an inverse function is, you do 1 over the derivative of the other actual inverse. Again, this sounds weird. What is f negative 1 really, though, in this problem? What was f negative 1 defined as? G of x, right? So this is really saying, if you want to find g prime of x, it's really equal to 1 over f prime of g inverse of x. That's the rule you want to write down. I know this rule is kind of weird. The proof of this rule, where it comes from, would take like 5 or 6 pages to actually go through. Did he show you the proof? No. Okay. Yeah, the proof is very, very difficult here. And this is a topic that I have never even seen on AP Calculus, but it's on the test. So this is what you want to write down. So let's go through this problem now that we know what to do here. The problem asks to find what? What does the very end of the problem say? Find?
Value of g prime of 2.
G prime of 2. Okay. So if I want to know what g prime of 2 is, all I have to do is think about the inverse of 2. Whoops. The inverse of 2, which is, okay, I'm going to...
It's not inverse of g, it's inverse of
Thank you. Thank you. Let's write it as inverse, though. I don't want to write it that way, so let's write it this way. Rewrite this, please, as f inverse of x here. Okay? Just because just because when we actually translate this, this is going to become g of x, not g inverse of x there. So, if we want to know g prime of 2, we do 1 over f inverse, or f prime of f inverse, right here. But f inverse is g of x, so this becomes now, the tough part of this problem is actually figuring out what to do next. Because if I plug a 2 in right here, it's really plugging a 2 in right here. But is g of 2 given in this problem?
Yes.
Is g of 2 given? What is it given as?
1.
As 1. Okay, so if we plug a 1 in here, now I want to know if g of 2 is given as 1, what is f prime of 1? What was f prime of 1 given as?
Why not?
Oh, primes? Oh,
Yeah,
yeah.
but
No, it's plugging these in.
The original is given.
The original is given, right?
Yes.
So what can you do with the original?
Right.
But the original is given, not f prime. The original is.
Derivative.
Take the derivative of the original, then plug a 1 in. This is f prime, guys. It's not f inverse, f prime. So here, once you know the value of g of 2, which is given, it's not always going to be given. There was another problem I was doing yesterday, it wasn't given. That's why I was confusing that. Your 2008 one, you'll see. So g of 2 was given as 1, so we plug a 1 in here. Then this says f prime of 1. So start with the original function, you take the derivative of that original function, and then plug a 1 in. Is this the derivative of the original, I think?
Yeah.
Right, that's what you get? I don't have the problem in front of me. So here's the derivative of the original. You plug in the 1 there, you're going to get 3 times 1, which is 1 plus 1 is 4. It's 4. 3 times 1 is 3, plus 1 is 4 in the 1. You're going to end up getting 1/4. Okay, I know that was really confusing. You want to do another problem on the side?
Yeah.
I think we should. That was very confusing. I'll make up a problem for this one. Let's say we're given,
This is not tough.
Yeah, he's working his way up to becoming me.
let's say we're given f of x is equal to g inverse of x, and we're told that f of 2 is equal to 3. We're told that f prime of 2 is equal to 4. And the problem says find g inverse of 3. Okay, find g inverse or g derivative inverse? Okay. Find g prime of 3. I'm trying to make it consistent with what the AP exam is. All right. So you're told that the integral that f of x equal to the inverse of g of x. We're told that f of 2 equals 3, f prime of 2 equals 4, and we're trying to find g prime of 3. Okay, g prime of 3. So if you're looking for g prime of 3, we have to start by saying g prime of x equals. Now from the last page, what do I write this as? 1 over? Well, what do we write down on the last page, guys?
You actually put f.
Don't put
Oh,
F.
wait, you put
F
f
inverse.
You put,
You put f
You put
prime,
GX.
parentheses f.
inverse.
The prime or
x.
inverse?
Thank you.
Either or.
I don't even have this rule memorized, guys. It's really sad. I don't ever, you don't ever use this rule, so I don't, I'm annoyed at why they're doing it.
Because he's saying, because inside, before it was
F inverse.
x, and f inverse x is equal to
Okay. Again, earlier we said this. Like that, right? Isn't that what we said earlier? Okay, so again, we're trying to find our g prime of 3. So this is the formula we're given. So it's f prime of the inverse of f. But the inverse of f is defined as g, really. And the inverse of g is defined as f. They're inverses of each other. So we start by replacing the f inverse with g of x. So far, so good? We replace the f inverse with g of x because they're defined as inverse functions. Now, if I want g prime of 3, I want g prime of 3. I need to plug in a 3 here, but the problem now is that that is not given. Everybody see that?
Well,
This is not given anywhere. I don't see g of 3 equals anything. Everybody see that so far? G of 3 is not saying anything anywhere. But I am given the fact that f of 2 is equal to 3. If f of 2 is equal to 3, then g of 3 is equal to 2. Why?
inverse.
Inverse. What's the definition of inverse? Back to algebra 2.
Y.
Isn't it just switching x and y? So if f of 2 is 3, then g of 3 is really 2. Because f and g are inverses of one another. So you're just switching the coordinates, really. So technically you are given this. By the way, this was on your homework last night, I think, right? Yeah, you would have to do this problem. So you plug in for g of 3 down here. So g of 3, this quantity right here, is really just 2. And we know f prime of 2, don't we? It's given as 4 there. So we then go down and say g prime of 3 equals 1 over f prime of whatever we just said. Thank you. 2. So again, g of 3 is 2 because they're inverses. So now we need to plug in f prime of 2. F prime of 2 is given as 4. So it turns out to be 1/4. Coincidence, same answer. I did not mean that. Okay, but g prime of 3 turns out to be 1 over 4. A lot of this is just manipulating a rule. That's why I hate the fact that it's on the exam. It doesn't take, there's barely any calculus involved here. Okay, I mean, I know you're doing the derivative and stuff, so there is calculus, but it really is just a rule. This is the question. Remember I said there's certain questions that a lot of kids don't do well on? And they give you percentages of the amount of students that get it right. This kind of a problem, it's like always like 10% of students get this right. Okay, so if you can get it right, it's good to do. But I wouldn't focus on this when I'm studying completely. I would know the rule and know how to apply it, maybe do some examples, that's it. But don't go crazy with it, because it's on maybe one question per test. Okay, I don't see this very often. You saw it on the 2003, which you have in front of you, and then the homework, which was the 2008, it was one question on there as well. But you're not going to see it very often. Okay, just to give you a little heads up. All right, let's go to the next one. 28. We did this one already, believe it or not. We already did this problem. Remember we did this in class? I did an example like it. This is where they're telling us, they tell us that g of 4, or f of 4, whatever it is, g of 4. G of 4 equals 12, right here. And g of 5 is equal to 18. Is it in the table value this time? This is told, right? Okay. You're told that both the first and second derivative are positive for all x. When the first derivative is positive, the function is increasing. When the second derivative is positive, the function is concave up. So that's my sketch right there. Now, if it's concave up, what kind of a graph am I thinking of here? Yeah, exponential or quadratic. Okay, I could also really think of like a sine and cosine wave. Okay, but that would be a little bit more confusing. It would look more like this and it would continue like that. Okay, but just think about the fact that it's growing pretty fast, right? How far does this graph grow between 4 and 5? How far does it grow? 6 units, right? Look at the y value change. Between 4 and 5, it grows 6 units. What is this problem asking us to figure out? Estimate what? The next point. So if I go another unit, I'm not going to go up 6 anymore because I'm growing faster. So how am I going to go up? How far?
The next biggest number. Well, from your answer choice.
Sure, but I want to know holistically speaking. If this were a line, it would go up 6, and then the next one will go up 6 again, right? But clearly it's increasing really fast. So how far is my y change going to be?
8, 10.
Holistically, I'm not asking for a number.
A lot.
A lot, short. We're not getting the point here. You're saying a lot, you're saying 8, 10.
It's big. No, it's bigger. It's not like.
Bigger than what?
More.
So bigger than what? What's the number? Bigger than? 6. Again, what was this delta y value? It was 6, right? So since I'm growing exponentially or parabolically, this now changed in y is going to be bigger than 6. If I just added 6 to 18, what do I get? 24, right? So my answer must be greater than 24. Again, if the growth had been linear, g of 6 would just be 24. Since my growth is exponential or parabolic, it's going to be bigger than 24. So if we look at this, The only answer that was bigger than 24 was choice E. That was the only one that was bigger than 24. Okay? All right. Flip over, please. Let's go to number 76, next page. The first problem, notice right away it's a velocity acceleration problem, right? Velocity acceleration. What are they asking us for at the very end of the problem?
Acceleration is
Good. Acceleration is what?
Second derivative.
Second derivative of?
Position.
Or the first derivative of? Velocity. Remember, acceleration is really defined as the first derivative. So if I didn't write it down here, I know I didn't, but acceleration equals v dot of t. Aren't you given v, everybody? You're given v, aren't you, in this problem? So go to y equals, and I'm going to do this with you because people are miserably failing this part, which baffles my mind. So we're going to go into this. We're going to go to our calculator. We're going to type in the function for v of t into y1. And we're going to do this whole thing together here. Come on, calculate, load. There it is. I'm going to go to my y1. I'm going to clear it. I'm going to go ahead and type in, what's my velocity function here?
3 plus 1.1 equals 0.9.
What mode should I be in?
Radian.
Thank you. Make sure you're in radian mode. I go to my mode, I'm in radian, I'm good. Before the test, check that out. So, that's my velocity function. I am not asked to graph, I'm not doing anything with graphing the acceleration function. I want to know the acceleration at a certain location. What location is that? 4. Very good. At time equals 4. So, press second, calc. Go down to number 6. And just press 4 and hit enter. That's it. That's the whole problem here. I want to know the slope of this curve at 4. Press 4, enter. There's your derivatives. -1 or positive 1.63. Okay, look at choice C. That's your answer. Again, when you're asked to find a derivative at a location, use the calculate function. When you're asked to graph a derivative, you go here, you go down to y2, you go to math, you go down to n deriv, graph n deriv, you go to y vars, go over to y vars, put y1 in there, comma x, comma x. That would graph the acceleration. This right here would be the graph of the acceleration. So if I turned off my velocity now, and I just say graph now, that's the graph of the acceleration function. So if you were asked to know when is the function increasing or decreasing, you would have to graph the acceleration, right? You would have to graph it and say, okay, well, if this is the acceleration, then the velocity is increasing from here to here. The velocity is increasing here, increasing here. The velocity would be a decreasing function in those time intervals. Because this is my acceleration here. If this is my acceleration, it tells me that when the acceleration is positive, the velocity is greater than 0, or the velocity, sorry, not greater than 0. The velocity is increasing. The velocity is increasing. The velocity is increasing because this is my acceleration here. Again, because this is my acceleration. All right, next one. We're given some regions here, and we're asked to find the integral from -3 to 3. Has to find the integral from -3 to 3 of f of x plus 1. So, start by thinking about your rules of derivatives. Break it up. Break this up into the integral of f of x plus the integral of 1. Because why? You're given this on the graph. Look at your graph in front of you. You're told that all the areas are 2, right? So you know that that area for A down here is really what? The integral. What is the integral from -3 to whatever this point is right here?
-2. -2.
-2, the integral. The area is 2. So the integral here is -2. The integral here is +2. The integral down here is back to -2. Add those up. What do you get? you get negative 2. That's this part right here. That's the first part of the integral. This part turns out to be negative 2. Then you just have to integrate 1 from negative 3 to 3. Integral of 1 is just x from 3 to negative 3. Plug them in. You end up getting a 6 here. Negative 3 minus negative 3 is 6. This is going to become positive 4. Again, my graph in this problem is really telling me that this area is 2, this area is 2, this area is 2. So the integral from the beginning to the end is negative 2, positive 2, negative 2. That's this part right here. Negative 2 from the area from A, positive 2 from the area from B, negative 2 from the area from C. Summing those areas up, I end up getting negative 2. That is the integral of this function. But it's not asking you to integrate the function. It's asking you to integrate the function plus 1. So you have to do this 1 as a separate integral for itself. And that should be easy. The integral of 1 is x. Just apply your limits. See what you end up getting. All right, 78. What kind of a problem is this? What is it? Related rates. Related rates. Okay, related rates. This is your insert. Go to your insert now. The one that was not on the test, okay? You took it on Saturday, it was not on the test. So we'll go over this together now. All right, can somebody read for us, please?
The radius of a circle is increasing at a constant rate of 0.2 meters per second. What is the rate of increase in the area of the circle at the instant when the circumference of the circle is 25 meters?
25. All right. So right away, I start by thinking about this as, all right, I'm given a related rate of dr dt. That's right here. Okay? Again, you're given that the rate of change of the radius is 0.2 meters per second. It says increasing. So what kind of a sign should I have? If it were decreasing? Good. So I start with the positive 0.2 there. Next, I then have to say to myself, I'm trying to find the rate of increase of the area. So what's the area formula? Pi r squared. I want to find the rate of increase. So I'm searching for dA dt. I know that dA dt equals, bring the 2 down, 2 pi r dr dt. Now, at first when I did this problem, I said, okay, I'm given the circumference is 20 pi. I actually solved for the radius and plugged it in here. But what did I write afterward? This or part. This 2 pi r location right here, what's 2 pi r really? Circumference. And circumference was given, wasn't it? That's 20 pi. So just plug in a 20 pi right here. Make this 20 pi. Get rid of what you see there, because that's what the circumference is. dr dt is 0.2. 0.2 times 20 pi. Again, 0.2 times really 20 pi, or 0.2 times 20 pi is just 4 pi. Okay, just 4 pi. All right, 79. 79 asks us, for which of the following does the limit exist as x approaches 4? Okay, as x approaches 4. I simply just wrote limits exist when the limit from the right and the limit from the left are equal. Look at the first one. They are both equal. They're both going toward the same location. They're going to the same target. Look at the second graph. They're both going to that same target, that open circle. And then look at the third graph. They're both going to different locations. So the first and the second graph have limits, thus choice D. Choice D. These need to be automatics, guys, these kinds of problems. You've got to get these right. It's just pictorial. That's all it is. The limit goes to that open circle. The limit goes to that open circle. These limits are different, thus no limit exists. A lot of the calculator problems they'll put in there, you don't even need a calculator for. It's happened for a long time, Cameron. I don't know why. We'll pick up with 80 after school. 80 after school. Yeah, please turn these back in, guys. Just put them in this folder on your way out. Just put them in this folder. You can keep your part 2s. You can keep your part 2s. All I need is the multiple choice again. I said it before. Okay, if you want to just pass them up, I can say.
Oh, that person, Karen.
Oh, yeah, you can.
Hold on, keep part 2s, keep part 2s. Oh, you can keep part 2s. I have your part 1s.
Can I leave my answer sheet inside as well?
Yep. Any multiple choice? Anybody else? Okay, we'll pick up from 80 after school. 80 right after school at 4 o'clock, please.